Okay, this last section. Shh. Hey, come on, folks. Shh. Shh. This is the last one. The first part is fairly easy. Second part isn't so easy. You want to pay attention. Page 554 at the top. The red letters there say powers of complex numbers. So we've talked about multiplying and dividing. You've practiced that with cis numbers. Now we're going to talk about taking them to a power, which is really just an extension of multiplying. Just multiplying a number by itself instead of a number by some other number. And so I'm not going to put any of this on the board. This is not that hard. Take a look at what they say there. If you have a complex number in cis form called z, and it is r cosine theta plus I sine theta, then z squared is going to be r cosine theta plus I sine theta times r cosine theta plus I sine theta. And you know how to do that. You take the r times the r, which is r squared. So the numbers, our radius is just squared, just like the z does, just like you're expecting. And then you simply add theta to itself. Right? And you would have cosine 2 theta plus I sine 2 theta. The 2 corresponding to the exponent 2. So that if you now took r squared times r, trying to get z cubed times, trying to get z cubed, you would take z times z squared we just got, and you end up adding theta to 2 theta, which is 3 theta, the 3 corresponding to the exponent 3. And the r is to the third. Does that make any sense to you? Seems reasonable, right? Again, like logarithms. When you power a logarithm, you end up multiplying the power times the log. So, the Moivre's theorem says this. If z is some r times cosine theta plus I sine theta, in other words, r cis theta, and n is any positive integer, meaning natural number, has to be whole, has to be positive, not zero. Then, z raised to that power, the complex number raised to that power is going to be r to the n times cosine n theta plus I sine n theta. And I want to know if that makes sense for anybody who's still paying attention to me.
Yes,
Like all off in your own tangent someplace. Does that make any sense?
Yeah.
And we're going to try it. We have 1 plus I root 3 to the third. Okay, first of all, this is not in cis form. That's the first thing you got to do is put it in cis form. Anybody? What would the radius be, or can you tell? Okay, wait. Let's draw a picture if that's what you need. They're both positive, so it's in the first quadrant. We're going to go out 1 and up root 3. Put a point. Connect it. Draw a triangle. 1, root 3. What's that going to be?
2.
2. Because it is 1 squared, which is 1, plus root 3 squared, which is 3, and 1 plus 3 is 4, whose square root is 2. Okay? What's theta got to be?
60 or pi thirds.
I like pi thirds. Does it say in the stem of the problem, give you an indication whether they want radians or degrees? No, they don't say, but yeah, the problem is worked out with radians. If you had degrees and they didn't tell you in the beginning of the problem when they were describing what the problem is, I would accept it either way. So we're going to go with radians, okay? We good? So I'm going to go with pi thirds there. Do y'all understand how to draw this picture and the information that it gives you?
I have one question.
All right.
If L wasn't like a special triangle, would we have a way to figure out, oh yeah, the inverse tangent, never mind.
Yep.
Good one.
You okay on this, or do you need further explanation?
Yeah, how is it?
Okay.
Why is it pi thirds?
Because any right triangle where the short legs doubled is the hypotenuse has got to be a 30, 60, 90. And the short leg times root 3 is the long leg. That's further evidence that that's what it is. Does that make sense or not? You double the short leg, you get the hypotenuse, you got a 30, 60, 90 going on. Okay?
Or if you don't know how to do that, then you just do the inverse standard, right?
Yeah. But it'll give you a decimal, and you have to be able to convert it to, you have to divide it by pi, and it'll show you it's 1/3. You could do that. Okay, did you bring an admit?
What?
Did you bring an admit in?
Me?
Yeah.
I wasn't ready.
You haven't been there the whole time, have you?
Yeah, she was.
Pretty sure.
It's Pocock that's missing.
I just
Okay.
knew that Macy would be.
I will adjust that when I'm done recording, because I'm afraid if I go somewhere else, it's gonna cut it off. Okay, so I wanna know, based on this and this drawn picture, is everybody clear that the radius is 2 and the angle is pi/3? If you have those two things, you should be able to convert this to cis form, which would be 2, parenthesis, cosine pi/3 plus I sine pi/3. And it is this that we wish to cube using de Moivre's theorem, which isn't that hard. De Moivre's theorem says that we should cube the 2, which is 8. And then when we get in here, side here, we should triple the angle.
Oh my God.
Did you figure that out? Now, since the problem was given to us in standard form, we should, now that we've used de Moivre's theorem on cis form, we should now return to standard form. This is how you do it. You have to evaluate this. What is the cosine of pi? -1 plus. What is the sine of pi? 0. And 0i is still 0, so the answer is -8.
Nice.
You okay on that? So you actually evaluate the result of multiplying by 3 because we were cubing. You have actually evaluate those things and then simplify it back to standard form. So what we're saying is 1 plus I root 3 is cubed is -8. Interesting way to go. Okay, here we go. Next one. They're giving it to us in standard form again. See if we can deal with it. I think you can see over that far. Next one has it in standard form. -√2/2 plus √2/2. I know I've got that in 2 different forms, but it's okay. We can handle it. Plus I times √2/2. Oh, we want to raise that to the 8th. It's not a big deal. What should we do first? Yeah, I think so too. Draw a picture.
45 degrees.
Let's see, we're going to go left and up, so probably second quadrant. Better draw this a little differently.
It's going to be.
We're going to go left this far and up just as far. Plot a point. Make a triangle. Whoever is talking, will you stop it? This is -√2/2. This is +√2/2, which means this is 1. And this reference angle is,
45.
you want to go with it, degrees this time?
Yes.
All right, that's fine. But the actual angle is
135.
135. That's theta. This is alpha. Okay, so we've got our angle 135. We've got our radius 1. Here we go. Using de Moivre's theorem, we're going to take 1 times, I'm going to leave the 1 there just to keep track of everything. And it'll be the cosine of 135 plus I sine 135 to the 8th. Using de Moivre's theorem means that we take the radius to the 8th power, which is 1. Okay, what is the, and then it'll be the cosine of, what's 8 times 135?
1080.
Okay, can you tell me what that is on the first go around of the inner circle? How do you find out what that is? Take the 1080 and you do what?
Divided by 360.
I would go
-360.
I would go -360, -360, -360 until you get a number that's between 0 and 360. That number's small enough to take that one.
60.
What is it? 360, it's 0?
Yeah.
Okay, so I'm gonna use 0. Plus I sine 0. Now that little process going from here to here was taking this times 8 and figuring out how many degrees that is between 0 and 360. Turned out to be 0 because 1080 is divisible by 360 evenly. So we're at 0 again. If you put 2 pi there, it works as well, although 2 pi isn't really, 360 isn't really included. When we do these range of values, it's always between 0 and 360, and the big one is not included. We put the 0 there instead, so this is appropriate. Now we've done the De Moivre's theorem. We've 8th powered this thing. Now we go back. What's the cosine of 0? What's the sine of 0? So this is 1. That thing to the 8th is 1.
Will they always come out one?
No, they just wanted to do this because it's kind of cool. No, they won't always come out that way.
How come it's not raised to 8 when it's in 10 parentheses? Like the cosine 135 is a big raised to 8, how come it's times 8?
We went over that at the beginning.
Yeah, I was confused.
Really?
Yeah.
Were you not following?
No, I wasn't, but I just don't know why.
If you were following, you'd know why. Look. If you have z equals r times the cosine of theta plus I sine theta, and you want to take z squared, that's z times z, which you've already practiced if you did your homework. If you didn't do your homework, I shouldn't be talking to you. You smile. When you multiply z times z, what you do is you take this, if you'll remember how to multiply, plus I sine theta, and you multiply by r times cosine theta plus I sine theta. And then when you multiply, you've got 4 things to multiply. R times R is R squared. When you multiply these together, we discussed this the other day, and if you didn't pay attention to that, I don't know what to tell you. You add the thetas.
There we go. All right, we're good.
Oops.
You
And this thing right here, the square, this, that thingy corresponds to that, and that, and that.
Perfect. Thank you.
Okay.
I didn't know you don't find some data, you just add.
That's kind of like logarithms.
Okay.
With logarithms, if you multiply 2 logs, you end up logging you end up adding the logs. So multiplication resorts to addition, division resorts to subtraction, and powering results to multiplication, which is what we're doing now. Multiplying that data. Very much like logarithms. Okay. Now we're going to do the last thing, and this is pretty hard to do at first. It's going to be a little bit uncomfortable, but stay with me. We are going to now go backwards because we've added and subtracted. That's what we did the first part of this section. We've powered. What's the inverse of powering? Rooting, not just square rooting, but rooting altogether in a general way. So that's the next thing in the red at the bottom of page 555. It says roots of complex numbers. So now we're going to go backwards and do the roots. And I'm telling you right now, the process doesn't feel like we're going backwards. So just go with me on it. I can prove it to you. It'll take a long time. I've got a big old paper that I can follow through, and I can show you why what we're about to do is how we root things. You want to see that?
No, we're good. I'll take your word for it.
Okay. Then understood that I could prove it if you wanted to see it. So trust me. And instead, go to the rather kind of orangish yellow box, orange band yellow box on near the bottom of page 556, because that's what the proof leads to. They've got the proof there for you after the red numbers or after the red letters on roots of complex numbers. Then they follow through and a little big long fat proof, and then they've got the result. We're going with the result. Is that okay? Here's what it is. For, this is the same thing for z, just like we just saw it. For z equals r cosine theta plus I sine theta. If you wish to take the nth root of it, the n distinct. This is going to be a little weird to you too. N distinct roots. Meaning, if you're trying to fourth root, you will get 4 answers. If you're trying to 10th root, you will get 10 answers. If you're trying to square root, you will get 2 answers. So, whatever you're trying to power it to, the nth distinct roots is what the index is on the root, okay? And it is this. You actually nth root r like you might expect. Whatever r is, you nth root it. To do the inside, you take the cosine of, and this is where it gets a little complex, the original theta plus 2 pi k over n, n being the nth root, the thing in the index, plus I sine of that same thing, which means that as soon as you figure out what this is, you can just write it over here. So you only have to figure it out once. It's the same angle, 2 pi k over n. That's the thing that you have to use, commit to memory, before the test. Okay? But you will use it enough on here. If you actually do your homework and try not to use that as a crutch every single time, you'll get it. I'm also going to show you another way if you're clever to get it. Another way to do it so that if you understand them both, you can check yourself and make sure you're correct. So here's an example. Find the 4th roots of 5 cosine pi thirds. 5 cosine. Is it pi thirds, did I say?
Yep.
Plus I sine pi thirds. Okay. We want to find the 4th roots of that. So we start out doing this. You just leave it like that. Since 5 won't 4th root, you just leave it. 4th root of 5, you want to put it in exact form, which I want you to. I want you to leave things in exact form. Then, and this would be the 1st root. Oh, by the way, I haven't discussed what k is. We need to know what k is. K actually starts at 0. So you're used to counting 1, 2, 3, 4, 5. We're going to start at 0, which means that k will take on the values 0, 1, 2, and 3. Because there are 4 roots. It starts with 0. So it's always 1 less than. So if I want to find the 1st root, the k value is 0.
Okay.
All right? And that would be the cosine of, if I'm following this exactly, pi thirds plus 2 pi times 0. I'm just following the recipe exactly. I realize you can do that in your head. Over 4, because that's n. See the n? You follow them? Plus I sine, and I'm not going to write all that out. I'm going to simplify this as I go. It's just going to be pi 12ths, if you think about it. It's pi thirds plus nothing divided by 4. Pi thirds divided by 4 is pi 12ths. So this is really pi 12ths. We're just following the recipe very carefully here, realizing that, and this would be the same thing. I simplified it over here. This is what I'm going to focus on. You all right with that? Okay. So I'm pretty sure, since we don't know anything about pi 12ths, that they want us to leave it in this form. It says, let's see, for number 7, find the 4th roots of this. And it looks like, if you look at the top of page 557, they're going to let us leave it in this form. So really what I should do to make this the case, I'm just going to make this pi 12 so that everything matches up and they all look right. Okay, so the second one, that was pretty easy because k was 0. The second root of 4 is going to be the 4th root of 5 times the cosine of pi thirds plus 2 pi, because k is now 1, divided by 4, plus I sine, and I'm going to figure this out. Here's your safest bet. Using your calculator, you can take 1/3 plus 2, hit enter, divide by 4, hit enter, and make it change it back to a fraction. You can do all the fractional crap in your calculator as long as you leave the pi out of it for now. 7 pi 12ths? Y'all understand how to use your calculator to do the fractional grunt work? You do? I hope. Okay. So I'm going to replace this. I wrote this out so I could calculate. Now I'm going to replace it with what it is. 7 pi 12ths. Okay, third one is going to be the 4th root of 5 times the cosine of pi thirds. Pi thirds plus 4 pi, because k is now 2. You with me?
Yeah.
Over 4. Okay, do the fractional work on that.
13 pi 12.
Okay, we'll replace this with 13 pi fourths. And I want you to notice something.
13 by 12.
What?
13 pi 12.
12ths. Thank you. Okay, I want you to notice something here because you may find this able to expedite your work. First of all, this will be the first angle divided by 4. Every time. Well, divided by whatever this index is. 4 right there. That's the operative thing right there. This will be whatever angle you're working with divided by however many roots you're trying to find. That'll be the first one. The second one you should probably find using the recipe. But everything after that will be an addition increment. 1 plus 6 is 7. 7 plus 6 is 13. 13 plus 6 will be the next one, over 12. 19? Yep. So the fourth root, without actually working this out, but instead observing the pattern, will be the cosine of this plus 6. Now, how did I decide 6? Because 1 plus something gave me 7. That's how. Right?
Oh.
19 pi 12ths, because I added 6 to 13, plus I sine 19 pi 12ths. And the reason why we don't go any further is because if I added 6 to 19 pi 12ths, it would be 25 pi 12ths, which is more than 2 pi, which means I've gone all the way around.
Wait, can you use this on this?
Sure. Fine. Can use this if it's wrong. You better be able to show me where it came from, maybe 1 or 2, and then you can just, once you realize what you're doing, you can just cis the rest. But I'd like to see that you can get started and follow the pattern. Okay? You okay on that first example then? Okay. I'm going to come back to this one. The answers are on page 557. I'm going to come back to it in a few minutes and show you, but I need to do one more so that the pattern that I want to show you becomes more evident. So we're going to have to refer back to this, but I'm going to have to erase it because I'm recording. We'll come back to the stuff they have on page 557. That's what we just arrived at here. Okay? Let's do one more of these, see if we can go a little bit faster now that you know what we're doing, using the recipe there. Okay? On number 8, on example at 8, it says find the cube roots of -1. What? Cube roots, that means 3. And it's just -1. And you're going, well, the cube root of -1 is -1. That's one of them. The other 2 are imaginary. Because when you ask yourself, when you're cube rooting -1, you may ask yourself, what number do I know of when I multiply by it 3 times gives me -1? The answer is -1. -1 times -1 is +1 times -1 is -1, right? But what you really should say in the context of this lecture is, what real numbers do I know of when I multiply it by itself 3 times gives me -1? And the answer is -1. That's the real solution. But there are 3. There are always 3. If you're doing cube roots. There are always 8 if you're doing 8th roots. And some of them are real and some of them aren't. But there are 8 of them. This one has 3. So what we need to do first is write that -1 like this. And then convert that to cis form. So we got a little bit more work to do here. We go out negative, well, I guess that'll be negative. We go out to -1 back here like this. What is the radius of that point? It is not.
Which is 1.
It's 1. What is the angle that spun it? Pi. So this thingy in cis form is going to be 1 times the cosine of pi minus I sine pi. That's the beginning cis form of this. Do you see how we arrived at it?
Why would it be minus I sine
Yeah,
pi?
why is it minus?
What?
Why is it minus I sine
I don't know. Should be.
Oh,
Okay, good.
I was gonna say, well,
I had the -1 on the brain. Sorry. It's plus. Okay, so this is our cis form. Now to the cis form we apply the nth root theorem. So we have the cube root of 1, which is 1. I'm gonna put down exactly what we're doing. We're following it, but I'm not gonna do that anymore after this. So it's the cube root of 1. That's what we do. And then the cosine of pi. Pi
2 pi 0.
Oh,
No, it's just gonna be pi thirds.
thirds. Yeah. The very first one's gonna be the angle we chose in the original equation, the original form, cis form. We're gonna divide it by what we're using as the index. You okay with that?
Yes.
Plus I sine pi thirds. Okay, that's the first root where k is 0. The next one's going to be the cube root of 1 times the cosine of pi plus 2 pi over 3.
So it's just pi again.
Just pi. We're back to there. Plus 2. This is the one that's going to give us the cube root of -1. This is the real one because this thing is landing at pi. That's 3 pi over 3, which is pi, which means we're right back to here, and this one's going to provide the real solution. You'll see. Okay, next one. I'm going to go ahead and make this a pi. What do we add to pi thirds to get pi?
2
Okay, so this will be the cosine of 5 pi thirds. Because if I add 2, if this is 1/3 and I add 2 to get 3/3, I got to add 2 to get 5/3. You understand the pattern? Without doing the arithmetic? You good? Plus I sine pi thirds, 5 pi thirds. Yeah, thank you. Okay, now these are all familiar angles. So we can take every one of these roots back to standard form. We didn't do so well on the other one, but this one we could. What's the cosine of pi thirds? I'm putting this here just to remind you that sometimes the radius isn't 1 and you need to count for it. Cosine of pi thirds is? Do you need to draw a picture?
Yes.
Yeah.
You okay with that?
Yeah.
So the cosine is 1/2. And the sine is?
Yeah.
Never mind.
If I take the 1 off, because in this case we don't need it, 1 times it is just that. That is your first imaginary root.
Yes.
What is this one? I'm leaving the 1 off again, but only because it's 1. If it were 4, you'd need it.
-1.
So it's going to be -1 plus 0i, which is -1. That's the one that's the real one that you anticipated. Cube root of -1 is -1. There. It's also 1/2 plus root 3 over 2i. What's this one? Cosine of 5 pi thirds. 1/2 minus root 3 over 2i. And those are your 3 roots.
So if it was a 4, you would multiply the 4 throughout those?
Yep. And it would cancel the 2's and you'd end up with something without fractions.
I'd be confused on the last one. Why isn't it -1 instead of?
5 pi thirds is here. Cosine is 1/2.
Yep. Sorry.
That's all right.
I was thinking it was in the second quadrant.
Oh, yeah, nope. Here's what I want you to notice, folks. This is pretty cool, actually. Because we were cube rooting, what we ended up doing is splitting the unit circle up into 3 parts. One sticking out there, one sticking out there, and one sticking out there. Where there's 120 degrees between each one because we were cube rooting. This location right here on the real imaginary grid, this point on the end there is 1/2 plus root 3 over 2i. That's that point. This one over here is -1. And this one down here is 1/2 minus root 3 over 2i. On the real imaginary grid, that's where those are.
If you were 6 through
Sorry about that.
Now, I want to go back. Now that you've seen how this fits on here, we split it up into 3 equal parts. Listen, shh, shh, shh. Starting at any one of them. So you really only need to find one. If you know that the cube root of -1 is going to be -1 for one of the roots, then start here. Go 120 degrees, put a point, figure out what it is. Go 120 degrees, get a point. Come back to here, and you have these points if you do that. So start with the one you know, or find one of them, and then split the circle up into this many pieces from there. Figure out how many degrees you got to go and go get your next point. Sometimes that's easy, sometimes it's not. For example, go back one page, go back to the top of page 557, the one I was going to remind you of. You're going, geez, I don't know where pi 12 plus I sine pi 12 is. I don't know where that is. I'll tell you where it is. It's an angle of pi 12 opened up. And what is 2 pi split up into 4 pieces? Pi halves. Now, think about the angles right there. Listen, started out in that problem that I was talking about that I said we're going to refer back to. We started out with when k was 0, we started out with pi 12ths, right? Which was pretty easy to come by because we took the pi thirds divided by 4, which is what we were 4th rooting. The pi 12ths was pretty easy to come by. If you split the unit circle up into 4 pieces, pi halves each, right? Then add pi halves to that. The angle in the second root. Add pi halves to that. 13 pi halves. The next one. Add pi halves to that. 19 pi halves. So what's really going on is we are adding pi halves to the angle each time and get all the way around. And this is what we actually have, folks, if you want to follow what's going on geometrically. We have a pi 12ths. Then we added to that, to this little guy right here that we opened up. We added pi halves. Now adding pi halves to this one straight out is this. So I got to go pi 12ths beyond that. So I'm now at that location. And then this location. And then this location where this angle is pi 12ths. This angle is pi 12ths. And this angle is pi 12ths. And the ends of these are the cis form or the irrational form, or the standard form. But it just, all it is, it said, I want to split this up into 4 pieces because we were 4th rooting. But by the way, the first one's pi 12, so the whole thing goes like that. All your pieces are at right angles with each other all the way around because we're adding pi halves, which is 90 degrees. So that's something to note and be aware of. You can check yourself on that. I like the geometry way better than I like this stuff. I can do them both, but I do that better and easier. It's up to you. If you like the algebra better and the recipe following that, that's great. Not a problem. Just giving you an alternate way to do it and the way that it lines up on the unit circle. It's great. Works out beautiful. Oh, and by the way, the radius is always the 4th root of whatever the radius is you started with or whatever root you're doing. So that's easy. Come on. You want to try one more? Yeah.
Will it always be your adding pi halves?
No, only if you're 4th rooting.
It's different for every.
You have to split the unit circle up into 4 pieces and ask yourself how big that angle is. When we're 4th rooting, that's what you divide 2 pi by. If we're going to be 6th rooting, you'd have to divide it up into 6 equal pieces and figure out what that piece is and add it each time. You understand? Okay. No, it will not always be pi halves. Okay, let's try one more. And this time, I want to do the geometry part. I want to do it geometrically first and then show you that it works out this other way if you wish.
Yeah, that's good.
Okay? The last one is to find the 8th roots of 1.
Let's go.
Look at the way they write it, though. Anytime in math you see the word unity, it means 1. So, in example 9, it says, find the 8th roots of unity. That means of 1. 8th roots. Remember we call it the unit circle whose radius is 1? Unity, because they're trying to get you used to vocabulary.
What's the point?
To get you used to vocabulary, because you may see it in other books, you gotta know what it means. Okay, the 8th roots of 1 is what that means. So, remember how we did it with -1? We first plotted that on the real imaginary grid. Well, it's right here. What's the radius of that? 1. Then we can ignore it, because whenever you power or root 1, you get 1. So we're going to ignore the radius because it's 1. You understand? Because it's 1 this time, the radius of that thing is 1. If it were some other thing like 5, we would have to 4th root it. But I'm going to be 8th rooting 1, which is 1, so I'm going to ignore it. You with me? Okay. And what is this angle? 0. So guess what, folks? This thing hasn't been spun this way. Nobody twisted it. It's starting right there. What do we have to divide the unit circle up into? 8 pieces. How big is that piece? Good. Then I'm talking about this one, this one, this one, this one, this one, this one, and this one. All of radius 1. What would this be then right here? What would that point be? If this is 1, it's 1 all the way around. Every time it's 1. Yeah, this point would be root 2 over 2. But since this is the real imaginary grid, that's what we're doing. This would be root 2 over 2 plus root 2 over 2i. And I didn't even go to cis form because I'm using the geometry directly. I'm able to go from standard form to standard form directly if you understand that we're splitting this up into 45 degrees each. And figuring out what that is based on that triangle. Root 2 over 2, root 2 over 2. This is real, this is imaginary. That's the point. You following me? Okay. So what would the next one be?
0
plus 1 plus I. Just I.
Here's that one. That's a 5th root. I'm sorry, that's an 8th root. What would this one be?
-2 plus 2 over 2i.
And this?
-1.
-1, and that's real. This one was imaginary because it was on the imaginary one. What's this one going to be? Minus.
Oh, and this one's going to be -i.
Yeah, and this one? Look at example 9 and look at the end result of all of those things. They may not be in the same order that we found them, but they're all there. Did we get a 1 at some point? That's the very first one. Did we get a root 2 over 2 plus root 2 over 2i? That's the next one, right? And then I. And then the second quadrant dealing with root 2's. Then negative, which was real. Then both of them root 2's, both of them root 2 thingies, they were root 2, they were negative because we're in the third quadrant. Then a negative I, pointing right straight down. And then a positive negative. And they're all there. Now, you need to see that definition or that recipe also provides the same things. Do you want to see that? If you need to see that, they've got it for you. Same page. Cosine pi fourths, then cosine pi halves, then cosine 3 pi fourths, sine all the way through, and you get all those things. It always generates those. So if you understand the geometry and you're starting in a reasonable place, you can always go these directly on the geometry for these. If they want them in cis form instead of standard form. That's what we found here with standard form all the way through. If they want them in cis form, you can still do this, but then you're going to have to realize the angle you're talking about here is pi fourths, the radius is 1, so it's going to be, this one is going to be cosine pi fourths plus I sine pi fourths. This will be cosine pi halves plus I sine pi halves. 3 pi fourths, 4 pi fourths, or pi, 5 pi fourths, 3 pi halves, 7 pi fourths. If you want to write them in cis form. You understand how the geometry all fits?
Oh, yeah.
These are standard form. If they want it in cis form, you're gonna have to do it geometrically and convert it to cis form, or follow this at the outset, because this is cis form. This is geometry standard form. You understand the two difference?
Yeah.
Yeah.
So if the radius were to be like, say, root 5,
Uh-huh.
or 4th root of 5,
8th root of 5 in this case.
how does that affect this?
I would put the 8th root of 5 root 2 over 2 plus the 8th root of 5 root 2, because you can't take an 8th root and a square root and combine them, especially if there's only 5 inside the 8th root. I really don't think they're going to do that to you. But if they did, I would just kind of distribute it, because this actually is an expression. It's not, notice it doesn't have a comma. This is an IJ form, if you will, kind of, sort of. It's where we add vectors instead of just put commas in between. We actually add them together. So you would need to distribute that through the expression, whatever it is, whatever R is. And if you can, simplify. For example, if R was 4, for some reason it was 4, then this would be 2 root 2 plus 2 root 2I, because the 2's would cancel in the distribution of 4. You know what I mean? But if it's root 5, if it's the 8th root of 5, you have to split it like that and then write it over. Okay, you want to give it a shot? I hope so, because I'm done. You have 13 problems to do. Sometimes you'll be powering things and sometimes you'll be rooting things. In either case, get the formulas memorized. There you go. See ya.